Alright guys, welcome to this tutorial video, and we'll be looking at number patterns, sequences and series. So we'll be looking at how to derive the formula for summing up the terms in a geometric series. So it's basically the formula that tells you that the sum of n terms in a geometric series is equals to a, which is the first term, into the constant ratio raised to the number of terms in that sequence minus 1, all divided by the constant ratio minus 1. Now let us do it this way. Let us think of a simple geometric series. Let's say we have the geometric series 2 plus 4 plus 8 plus 16 plus 32. Now let us see, when we sum up those terms, what do we get? When we say 2 plus 4 plus 8 plus 16 plus 32, this is supposed to give you a 62. So you get 62 as your answer, right? And of course, this is a geometric series, because let's look at it. If we say T2 divided by T1, we have that it's 4 divided by 2, which is equals to 2. And then when we say T3 divided by T2, we get an 8 divided by 4, which is equals to 2. So because we get the very same value there, we can therefore say this is geometric series because we have a constant ratio of R, which is equals to 2. Okay, now let us keep that. We are going to keep the R, which is equals to 2. So in that sequence, our ratio is equals to 2. Now here's how we will approach this. First of all, how many terms do we have? 1, 2, 3, 4, 5. We have the sum of 5 terms, which is equals to 2 plus 4 plus 8 plus 16 plus 32. We will then say, we'll then look at what happens if we take all these terms and multiply them by the constant ratio. So it's more like saying R multiplied by the sum of 5 terms. So each and every term is going to be multiplied by that constant ratio. But we already know the constant ratio to be 2. So we can just change that and say 2 multiplied by sum of 5 terms. So when we take this term, the first term, which is 2 multiplied by that 2, it gives us a 4. So we will then shift it to the right and write it to the corresponding digit, which is 4. 4 should correspond to 4. Then we take the second term, 4 multiplied by 2, it gives us an 8. So we write it to the corresponding one, which is 8. Then we take 8 multiplied by 2, it gives us a 16, corresponds to a 16. 16 multiplied by 2 gives us a 32, so we write it there. Then lastly, we have 32 multiplied by 2, which gives us a 64. As you can see, it doesn't correspond to anything. We will then say what happens. Okay, we have this as our first equation and we have this as our second equation. We will then take equation 2 and minus equation 1. When you take equation 2 and minus equation 1, on the left hand side you have 2 sum of 5 terms minus the left hand side for the first equation, which is sum of 5 terms. This should give you, here you have a 0 minus what? It's a 0 minus 2, which gives you minus 2. Then you have a 4 minus 4, which gives you a 0. 8 minus 8, which gives you a 0. 16 minus 16, which gives you a 0. 32 minus 32, again it's another 0. 64 minus 0, which is plus 64, right? So when you say 2 sum of 5 terms minus sum of 5 terms, it gives you sum of 5 terms. Here we have a minus 2 plus a what? A 64. But then when you say minus 2 plus 64, it gives you that this is equals to 62. Now if you look at this value, it's the very same one we got when we punched this into our calculator, right? So now I want us to come up with a way to treat this in variable form. Here's what we need to remember first. We need to remember the fact that in a geometric series, the first term is known as A, the second term is known as AR, the third term is known as AR squared, right? And so on. So we will use the variable form of that equation. We will then say, instead of having sum of 5 terms, we'll say it's sum of n terms because we don't know how many terms are there. What is the first term? The first term is A plus. What is the second term? The second term is AR. What is the third term? The third term is AR squared plus. The equation continues like that, as you can see, until it gets to AR to the exponent n minus 1. Remember, in a geometric series, in order for you to find any term in the sequence, it's calculated by the formula, which is Tn is equals to AR to the exponent n minus 1. So in order to find any term any term along that sequence, you are going to use that formula. So the last term, which is Tn in this case, is calculated by that formula there, right? Does it make sense? It should partly. And then from here we are going to introduce the very same thing and say, now what happens if we take each and every one of those terms and multiply it by AR? Remember, here we took the 2 and multiplied by the R, which was 2, and it gave us a 4. So when you take A multiplied by the R, remember we should shift it forward. When we shift it forward, it gives us A times R, we get the AR which corresponds to that. And then AR times R, we get the AR squared, right? Plus the sequence continues to the right. And then when we multiply again, we are going to have a term that will correspond to the AR to the n minus 1, just like you've seen, right? But now let's find out what happens if you take AR to the exponent n minus 1 and you multiply it by R. Remember, the laws of exponents tell you that when the bases are the same, you add the exponent. So it's AR to the exponent n minus 1 there plus the 1 there. So since you have that this is a minus 1 and a plus 1, it should give you an ARN to the exponent n, ARN to the n. So when you take this and you multiply it by an R, it should give you none other than an AR to the exponent n, as you can see there. And then what did we do from there? We then said this is going to be our equation 1 and this is going to be our equation 2, right? We said equation 2 minus equation 1, and then on the left hand side we have that this is RSN minus on the first one, which is Sn, which is equals to, remember this, we have a 0 minus a, which gives us a minus a, right? Is it? And then we have an AR minus AR, which is a 0, an AR squared minus AR squared, it's another 0, plus continues all the way. This minus that will give us another 0, plus this minus nothing will give us an AR to the exponent n. And then from there, what do we have? From there we have that this is going to be none other than, there's a common factor between these two of Sn. So when we say Sn, we have Sn into R minus 1, which is equals to, we can rearrange this and start with the positive term. As you can see, those ones are zeros. In fact, we should have had a minus a plus AR to the exponent n. So let's rewrite this term and have it in the form of, start with the AR to the n minus a. So from here, let's factorize what's common there. Is Sn into R minus 1. What's common between the terms of the right hand side is the a. So we have a R to the exponent n minus, when we take out the a there, we are left with the 1. So we have Sn, which is equals to a into R to the exponent n minus 1 divided by R minus 1. So that's how you derive this equation, which is used to calculate the sum of terms